In the previous video, where I discussed the kinetic molecular theory, I said that the average kinetic energy is proportional to temperature. Here, we will start at an equation that shows this, and then move on to ways in equations to describe the speed of gas molecules. Also, we'll see two ways the motion of gas molecules can be observed by experiments in diffusion and effusion. We'll see equations for these terms, and we'll also see some examples. Yeah, so this video will be pretty chock full of information, but we'll go through it fairly efficiently. The first thing is that kinetic energy, or average kinetic energy, is proportional to temperature. And the equation that I would use to quantitatively show this is that Ke average equals 1/2 mv squared, v for velocity. I'll put this into a box. Okay. Next is that the mean square speed, let's say v squared, and we'll take the average, is actually the summation, right? The summation of all the molecules' speeds. So the summation of all the speeds that were squared divided by the number of molecules. We won't be using this equation to solve for any numerical value, but we will use it to help derive other equations. Now, from the kinetic molecular theory, the KMT, one can derive this equation. For mole gas, 1 mole gas, the total kinetic energy, and I'll put TOT, equals 3/2 RT. Now, I'm not sure how this was derived, but it is related to postulate 4 of the kinetic molecular theory. What we will need to know is, and what we'll be using a lot in future topics, is the R. This is called the gas constant. And the gas constant R equals 8.314. The units are joules per mole dot K. So here we get the kinetic energy in joules. Actually, the kinetic energy here, you could tell, is M is kilograms. We've seen this before. Kilograms, and then V is meters per second, but remember it's squared. So the kinetic energy is in kilograms dot meter squared over second squared. Okay. And that is joules. So you may recall this from Unit 1. kg, oh here it is, dot m squared over v squared equals 1. That's the definition for a joule. Is there anything I want to box? Yeah. No. Just remember that your R constant is this, and your conversion is such. Now, well, if we're solving for actually, v, velocity, that is called the root mean square, right? Root mean square speed. And I'll write it down here. Root mean square. So the abbreviation is RMS speed. That is our title of today's video. The equation is, again, we have this velocity, and it's designated RMS equals is going to be the square root of 3 RT, okay, coming from, whoops, there, divided by actually the molar mass. And sources indicate molar mass differently. Some just show one capital M. I'll put 2 capital M's. We're going to be using this molar mass in a different equation later in this video. Okay, let's square that off. This is going to be an important value, and the equation we're going to derive that actually relates speeds of different gas molecules is also going to be important. Now, let me show you, I printed out what's called a, by the way, remember the KMT? Although many scientists were contributing to this, the 2 main scientists were Maxwell and Boltzmann. Well, they came up with what's called, or were using their ideas to create what's called a Boltzmann-Maxwell distribution. So we're going to see graphs in just a bit of, oh man, this is double N. Let me just double check. I don't want to misspell names. Let me look at real quick on my phone. Boltzmann-Maxwell distribution. It's a way to graphically show the speeds of molecules, and oh, very interesting. It's Maxwell first. Yeah, let me change that. Maxwell, Boltzmann distribution. Okay, let me show you 2 graphs. Both are considered Maxwell-Boltzmann distributions, and there are a couple of things that you want to know about these graphs. The first one is speed of the molecules in meters per second, 0 to 1500. Okay, that's your range, and then the number of molecules. Now, the thing is, they are comparing, in this case, comparing N2 gas at different temperatures. N2 gas. Gas at different T. The other thing that you want to realize is that the area underneath the curve of each temperature is identical. The area under curve is identical. Basically, the area carved out by these curves. So the area of this yellow, that's the same area as underneath the orange, underneath the red. We're just distributing the molecules differently. And we're going to say the area under is identical because we want to compare the same number of molecules per sample. Okay, what do you notice about this? At 100K, the very tippy top right here corresponds to a temperature of maybe around 200. Okay, for now we're going to call that the average. Not the root mean square average, but just the average. I'll be more precise with my language in just a bit. But I want to first figure out trends. So as we raise the temperature, to see how the temperature, the peak shifts to higher temperatures. And we go up to 700 and it shifts even higher. Okay, so that makes sense. The higher the temperature, the higher the speed. We knew that kinetic energy average is proportional. Is proportional to T. And yes, do we have that equation? We have this equation right here. So I say total. This is average when we use this equation right here. Okay. And yeah, as the temperature goes up, the speed, and I'll just say speed for now, goes up. I think that's pretty obvious. Take a look at the second graph. The second graph is comparing three gas molecules. It looks like chlorine has the slowest speed, followed by nitrogen and 2 gas, followed by helium. Oh, did I say slowest? Chlorine has the slowest speed, nitrogen is faster, helium is the fastest. And you remember that in the previous video I said smaller, or you could say lighter, molecules move faster. It still follows a Maxwell-Boltzmann distribution. Okay, so it's not symmetrical. It kind of tails off on the on the right. Okay, and you get this tail with faster and faster molecules up to a limit. Okay, now I want to use language a little more precise than what I've been doing so far. Where am I going to put this? Let me put this down here. Let's draw another Boltzmann distribution. And like I said, it's not symmetrical. There's a tail to the higher speeds, and the y-axis is number of molecules. Okay, so whether you're looking at different temperatures or looking at different gas molecules, the general shape is this. Oh, that came out better than I expected. And language. Let's be a little more precise. This top point here, just call that the VP. And VP is the most probable speed. Makes sense. We have the most molecules for each individual speed at this point, this speed. So VP is most probable speed. Most probable speed. We haven't seen the RMS yet. A little bit to the left. Sorry, a little bit to the right. Okay, I'm not showing you exactly where, but that is the average speed. And you have that bar on top of it. So V average, average speed. That makes sense because, like I said, it's not symmetrical, and you have some of these molecules that are going really, really fast in this tail. So that kind of shifts the speed to the right. Now we get to the VRMS, and that's also a little bit to the right of the average speed. And this is, what's the abbreviation? VRMS. VRMS. That is a root mean square speed. And that's typically the one that people are most interested in. Root mean square speed. It's a weighted average, so it gives more emphasis to the molecules that have a higher speed. We could also think of it as this was derived from equations about kinetic energy. So this is the more important of the three. It was derived from equations with dealing with kinetic energy. Okay, just remember that graphically. what the different types of speeds can be observed. Okay, next, we're going to take the VRMS and compare two different gases. If we have the VRMS of gas number 1, again, that is going to equal to square root of 3 RT, and it's to its molar mass. Well, if we want the ratio of the two speeds of two different gases, well, we'll take the ratio. So the ratio here is VRMS for molecule 2. Give me 1 second. Equals. So we take now situation 2, 3 RT MM, and we'll make this 2 and make this 1. Okay. So the thing is, this simplifies, right? And this simplifies to the RMS of 1 over the VRMS of 2 equals. So if you do the math and you do the correct canceling out, it's actually the square root of mm of 2 divided by the square root of mm1. And then let's think if that's true. Because we said that the lighter gas moves faster. So if, let's say, the lighter gas is 1 and the heavier is 2, does this make sense? Well, look, the square root of a smaller number is in the denominator. So this ratio right here is greater than 1. And then this ratio, right? Because the lighter gas is moving faster, so it has a higher speed. This ratio is greater than 1. Okay? Now, we're not going to use specifically RMS. There's a law called Graham's law, and it's the same format, Graham's law, but we're going to think of these now as rates, and you can think of rates as speed, like driving to school 50 miles per hour. That is my rate, that is my speed, and Graham's law formally is this: rate, and instead of using 1 and 2, I'll say rate of gas molecule A over rate of gas molecule B equals the square root of, now we take the inverse, molar mass of B over molar mass of A. And when you work out problems using this equation, I'll give you one, I think, very useful hint. If you have a choice, okay, make the lighter, faster gas, make it A, because that will give you a ratio of rates that's greater than 1. And then you could say that gas A is 2.9 times faster than rate B. So typically when we're doing problems with this equation, you're looking at relative rates. How much faster is how much faster is molecule A over molecule B? We could use their molecular weights, and I think we'll have time in a problem we're going to solve for the molecular weight. Did I say weight? That's what organic chemists say, molecular weight. We're going to solve for molar mass for these gases. Okay. So, I mentioned there are two processes, effusion and diffusion, and actually we'll look at diffusion first. Very simple. Diffusion is the mixing of gases, and we could relate the rate to how well they mix. And often this Graham's law is called the diffusion law. Diffusion law. The setup that is most common when you're looking at the diffusion of gases is something like this, where you have like a valve here that's closed at first, and you have two gases. We'll put gas A here and gas B here. Okay, and you open up the stopcock, and the gases mix, and you monitor how fast the gases mix. We'll actually see a little bit later an experiment like that. Effusion is very similar. It's how it passes through a pinhole, how gas passes through a pinhole. I'm going to try to draw this 3D. From one side of the container. Oh, that turned out much better than I thought. And into a vacuum. So this is a vacuum. And here we have our gases. Whoops. And their gases are going this way. You could think of effusion as how gases escape into a vacuum. Diffusion and effusion. So let me show you, or set up an experiment, and I'll show you the schematic in just a bit. If we take, if we take HCl plus ammonia, we actually get a salt. So both of these are gas. The salt is NH4Cl. And actually it's an ionic salt, or just a plain salt. Okay, but the fact is it is a solid and it's white. So the experiment is dip cotton balls in hydrochloric acid, dip a cotton ball in ammonia, stick it on two ends of a tube, and see where the white powder forms. Okay, which do you think moves faster, HCl or NH3? Well, the molar mass of HCl is 1 plus, chlorine is pretty heavy, 35, where ammonia is 14 plus 3 hydrogens, so that's about 17. This is lighter. Okay, it has a smaller mm. So we should think that this moves faster. Okay. Let me show you how to set up this experiment in the lab. And there it is. Do you see the white powder that's being formed? It's not in the middle. It's closer to the cotton ball on the right. My question here is that which cotton ball has HCl and which cotton ball has NH3? Okay, we said that NH3 is lighter and moves faster, so this traveled farther than this gas on the right. So I would predict that ammonia is the cotton ball on the left. It moved faster and it met the HCl closer to the HCl because HCl is moving slower. That's how you could interpret that experiment. Last thing. Okay. I want you to review the notes that we went over in this video and try this problem right here. Okay. The hint one more time is make the lighter, faster gas A in this equation. Okay, do you want to pause and check this out? It's asking you, what is a mystery gas if you know that helium moves 3.16 faster than that mystery gas? And if we know the molar mass of this mystery gas, maybe we have a way to figure out what is the molecular formula of that gas. Hint, it is a component of air. Why don't you pause the video and take a shot at this? Okay, welcome back. When I do an exam problem, I do get nervous. So I'm going to write down something visual, something that I know is true, and possibly I might use. Not 100% sure, but I think this is an equation that might be useful. Okay, because visually, now do I have enough variables that I know the numbers for? So how do you interpret this? First of all, we need the mystery gas, and we could get the mystery gas if we know the molar mass. We interpret 3.16 as the faster gas rate is 3.16 faster than the rate of the slower gas. So since this is faster, I'll put a little note to myself that He, helium, is A, and then question mark is B. Just plug in the numbers. Well, we have an unknown, and the unknown is B. So the unknown here is the molar mass of B on top, and that's the unknown. And then the molar mass of helium, A, is 4.003. Now hopefully you have the setup like I do. Now let's see if I can punch in the numbers correctly on a calculator. So the way I would do this, without doing a lot of writing, is I would take the square root of 4.003, 4.003 equals. Multiply it, cross multiply by 3.16 times 3.16 equals. What that equals is the square root of this. So what do? We square both sides? Yeah, if we square both sides, we'll get the molar mass of B. So that number squared? Okay, molar mass is 39.97. We'll round it to 40.0 grams per mole. Air is nitrogen, argon, and 2, right? You know, nitrogen is diatomic. Argon is not diatomic. Oh, is it argon? Could be argon. Actually, I'm a little surprised it could be argon. Argon has a molar mass of 39.95. What else is in air? Oxygen. Oxygen is 32 because it's O2. Carbon dioxide, 12.01 plus 16.00 plus 16.00. Oh. CO2 is equal to 44.01. Let me double check my math. Helium, okay. Square root. I thought it was carbon dioxide, to tell you the truth. Did I do this wrong? Okay, times 3.16, and that is squared. Oh, it is argon. It's argon. Circle that. Very interesting. I will double check. I thought it was going to be carbon dioxide, but we'll go with argon. Double check my math on your own, and good. That is information about different ways to get the different speeds, how to look at it graphically, and how to use Graham's law, in this case, to figure out what the mystery gas is.